The first thing I'm going to start with is the physiology of the respiratory system regarding respiration itself. Now, when we talk about respiration, a lot of times we think that we're actually talking about a ventilatory rate. Now, respiration, by definition, actually means that we are moving molecules from one area to another area across a pressure gradient, usually through a semi-permeable membrane. So it's kind of a misnomer whenever we say that we're getting a respiratory rate on a patient, when in reality we're actually getting a ventilatory rate. Respiration deals with the actual movement of molecules. So there are three types of movement of molecules. There's going to be external respiration, internal respiration, and cellular respiration. When we talk about external respiration, what we're actually talking about is the exchange of oxygen between the lungs and the outside air. So we're talking about exchange of oxygen between the lungs and outside. Or, of course, the atmosphere. That's supposed to be a D. And the atmosphere. So that technically is external respiration. This is what we refer to as a ventilatory rate. Internal respiration is a little bit different. It actually deals with the exchange of oxygen between the blood and tissues. The third type of respiration that we actually have on a regular basis is something called cellular respiration, and this might be a little bit more familiar to people who have had advanced biology classes and that kind of stuff when we talk about cellular respiration. Cellular respiration is actually the usage of oxygen by the cells to make energy. That technically is cellular respiration, and we actually do call this something different. We actually call this cellular metabolism. That is actually cellular respiration. First thing we're going to talk about is this gentleman here, Evangelista Torricelli, who was an Italian physicist and a mathematician who actually discovered the principle of the barometer in the 17th century. Now, what he actually did to come up with this is he performed a little experiment. First of all, he took a hollow tube, which is basically this thing right here all the way down. He took this hollow tube and he filled it with mercury. So he turned it upside down and he actually took this hollow tube, just like this, and he would fill it up with some mercury up to a certain point. Then he would take an empty beaker. This one actually has fluid in it, but he would take an empty beaker. He would take this tube and quickly flip it upside down and stick it into an empty beaker. When he did that, the mercury would run out of the hollow tube and actually start to fill up the beaker. Now, when he did this at sea level, he actually found that there was a certain amount of fluid that would actually leave the hollow tube and fill up the beaker, and then it would always stop. No matter where he was at sea level, no matter what part of the beach or anything he was at, he was always running out and then stopping at the same time, the mercury was. What he did then is he actually went up into the mountains. And when he went up into the mountains, he found that if he performed this exact same procedure where he filled up the hollow tube with the exact same amount of mercury, and he quickly flipped it upside down and stuck it into the empty beaker, what he found was quite fascinating because more mercury actually ran out of this hollow tube. So what happened at sea level was that the mercury went down further. When it happened in the mountains, the mercury actually ran down further. What he did to actually gauge this is he took this hollow tube and he actually graduated this tube in millimeters. So he had 0 somewhere up here, and he probably had another number somewhere down here. So what he did was he actually at sea level would flip this upside down, and the mercury at sea level would actually stop at 760 millimeters. Since he was using mercury, it's called millimeters of mercury, which is the standard that we use today for blood pressures or any kind of pressures in the body. We always use the standard millimeters of mercury. he concluded that if he was at sea level, since there is more air pressure at sea level, the air pressure here would actually push down on the fluid and prevent fluid from coming out of the hollow tube. So if he went up in elevation, there was actually less air pressure, so it wouldn't apply as much pressure down here on this fluid here on the mercury, which allowed more mercury to actually exit the hollow tube before stopping. Over time, it just became a standard that 760 millimeters of mercury came to be a standard atmospheric air pressure at sea level. Of course, in Las Vegas or up in the mountains anywhere, you're going to have much less air pressure. So for years, this was a very standard practice. And John Dalton, who is actually a giant in the science industry, came up with a law. It's one of Dalton's many laws. One of them is the pressure exerted by a mixture of gases is equal to the sum of the partial pressures of each, and each gas acts as if it were present alone. So first of all, let's talk about the pressure itself. So we know that the pressure of all the gases in the atmosphere at sea level equal 760 millimeters of mercury. Now, we have a whole bunch of gases in the atmosphere. We have nitrogen, oxygen, carbon dioxide, all kinds of other gases, humidities, and everything. All of the gases have to equal 760 millimeters of mercury. So, if you were to look at all the other gases here, nitrogen is actually the most abundant gas that we have in our atmosphere. Nitrogen accounts for 78% of our atmosphere. Now, if we know that nitrogen is 78% of our atmosphere, and we know that 760 millimeters of mercury is the air pressure at sea level, then all we have to do is multiply 760 times 78% of the atmosphere. And what we actually end up with is nitrogen accounts for about 592.8 millimeters of mercury, which tells me that of the 760 millimeters of mercury of pressure in the air right now, 592 of it is just nitrogen all by itself. We also know that oxygen is 21% air pressure, so we know that wherever you are, if you're up in the mountains or if you're at sea level, you always have oxygen is about 21% of the atmosphere. So if we multiply 760 times 0.21, which is 21%, we actually come out to oxygen being 159.6 millimeters of mercury. On average, we actually just say that oxygen is 160 millimeters of mercury. Carbon dioxide, on the other hand, only accounts for 0.03% of the atmosphere right now. So if you were to take 760 and multiply it times 0.00003, what you actually end up with is carbon dioxide only accounts for 0.2 millimeters of mercury of pressure of the atmosphere. Very small amount of carbon dioxide by itself in the atmosphere. Other inert gases in the atmosphere, humidity, and that kind of stuff actually count for all the other gases. All of the other gases is actually 0.97%, so less than 1%. If you multiply that 0.97% times 760, the number that you're going to come up with is actually 7.4 millimeters of mercury. If you were to add 78% plus 21% plus 0.03% plus 97%, you're going to come out to total gases equaling 100%. If you also add 592.8, 159.6, 0.2, and 7.4, you're actually going to come out to 760 millimeters of mercury. And many people have the question, why do we even care about something like this? Well, here's the issue. Oxygen and carbon dioxide get into and out of the respiratory system through diffusion. Diffusion actually requires pressure gradients to move gases through membranes. The greater the diffusion, the greater the pressure gradient. The less the diffusion results in less pressure gradients. So we do know that 21% of the air is actually oxygen by itself, which tells us that if we actually look at the PaO2 at the lips, we know that it's about 160 millimeters of mercury at the lips itself. Unfortunately, the PaO2 does not stay the same as it travels down to the alveoli because of warming and humidification, which is basically water molecules developing or present actually in the lungs themselves. What happens here, water vapor increases from 5.7 millimeters of mercury to 47 millimeters of mercury in the lungs themselves as you travel from the outside down into the lungs themselves. So because you now have changed your pressure of humidity from 5.7 to 47, you still can only have a max of 760 millimeters of mercury. You can't go any higher than that. So if you change your water vapor from 5.7 to 47 millimeters of mercury, something else has to give, and all the other gases actually drop in their pressures, including oxygen itself. Plus, there are also gases in the dead airspace of the lungs. These gases actually account for 150 milliliters of air, and a lot of times it's CO2 that it will actually mix with, as well as other gases. So at the alveoli, well, at the lips, we know that the pressure at the lips is 160 millimeters of mercury. As all of this process right here occurs, the PaO2 will drop to just about 104 millimeters of mercury. Whenever the blood comes by this alveoli right here, the blood PaO2 coming into the lungs is actually at 40 millimeters of mercury. What will happen here is as the blood passes the alveolar sac, the blood PaO2 will change from 40, it will actually increase to about 104 millimeters of mercury, and it will continue to diffuse until an equilibrium is actually met. Once oxygen gets into the bloodstream, it's actually transported to the tissues two different ways. Primarily, it will be dissolved in plasma, and it will be attached to the hemoglobin, creating a molecule called oxyhemoglobin. Dissolved in plasma, only 3% of the oxygen is actually dissolved in the plasma, which means the other 97% that travels through the bloodstream has to attach to hemoglobin to create oxyhemoglobin. That's why if you have low levels of hemoglobin, you don't get very much transport of oxygen because a very small amount of it is actually dissolved in the plasma. Hemoglobin should be fully saturated if the PaO2 in the blood is 80 to 100 millimeters of mercury. Now, if you remember on the previous slide, as the blood vessel goes by the alveolar sac, what will happen is it comes in and the PaO2 is 40. Inside the alveolar sac, it is about 100. So it will reach an equilibrium of about 100. As the blood leaves the alveolar sac, it will be about 100 millimeters of mercury. So if it's between 80 and 100, then you should have a hemoglobin which should be fully saturated. If you have fully saturated hemoglobin, what that means is that your SpO2 or your pulse oximetry should equal 99 to 100%. So if you have a pulse ox that you know you have a 99 to 100%, then you know that 80 to 100 millimeters of mercury of PO2 is actually in the bloodstream. So let's go ahead and look at this picture here, and hopefully this will help kind of explain everything. Blood leaving the pulmonary capillaries. So we're actually going to look up here at our alveolus. Here's our alveolus right here. If you actually look at the PO2, we have our PO2 at 60 millimeters of mercury. Now, as it goes down into the lungs, it is going to mix with other gases, humidity, carbon dioxide, that kind of stuff. Now our PO2 is actually down to 104. Our PO2 is constantly at 104 in the alveoli, so as the blood oxygenation comes by, it will start to diffuse oxygen until the PO2 actually reaches 104. So the blood leaving the pulmonary capillaries, if we leave the pulmonary capillaries here, the blood will actually be at 104. So blood leaving the pulmonary capillaries is 104 millimeters of mercury. Unfortunately, as the blood travels through the cardiovascular system, as it travels down through the heart into the rest of the cardiovascular system out to the system itself, you also have lots of mixing with shunted blood or deoxygenated blood as it's going out to the tissues, which means by the time that the blood reaches the capillary bed, you are no longer at 104 millimeters of mercury. You are now actually at 95 millimeters of mercury. But that's okay, because if you remember from the last slide, a PO2 of 80 to 100 is an SpO2 of 100%, which means that your hemoglobin are still fully saturated. So blood arriving to the systemic capillaries is a PO2 of 95 millimeters of mercury, still within a very good range to make sure that all of our hemoglobin are fully saturated. Now that the blood is down here near the tissues, you will have another diffusion that will occur from the capillary bed into the interstitial space and then continuing into the cells themselves. Now, what's interesting about this is that the PO2 in the interstitial space is always going to be 40. It doesn't go up and it doesn't go down. The PO2 inside the cells, on average, is about 20 millimeters of mercury. It never goes up and it never goes down. So what happens is you will then have a diffusion gradient that always travels from the capillary bed to the interstitial space down to the cells. You will always have that particular diffusion gradient of oxygen because oxygen is needed for cells to perform aerobic metabolism. Now, the blood that goes across this interstitial space here, it will keep diffusing blood until the PO2 is equal to the interstitial space. Now, this number should look familiar because if you look at the top of the screen here, this is where your PO2 started as it actually went into the capillary bed in the lungs. That comes from, if you look at the bottom of the picture now, that comes from the PO2 becoming an equilibrium with the interstitial space itself. So diffusion moves oxygen from the capillaries into the tissues until an equilibrium of 40 millimeters of mercury is met, and then it will travel back to the lungs. The cells continuously use oxygen only because of the fact that they are continuously performing cellular metabolism to create energy. That is why the PaO2 in the tissue is always so low. So what does that actually mean for us here in Vegas? Well, if you actually were to look at the chart here on this slide, at sea level at the lips, what is your PO2? It is 160 millimeters of mercury on average. If it travels to the alveoli, you lose about 35%, which means at the alveolar level, you actually have a PO2 of 104 millimeters of mercury, which means at the tissue level, your PO2 drops again to 95 millimeters of mercury. Now, you still will have plenty of saturation of the hemoglobin. Plenty of oxygen will actually be able to get down into the tissues themselves. Well, let's adjust this a little bit for altitude. Let's say for a second that somebody is up here in Vegas, and they are actually breathing the air in Vegas. And let's just concentrate on the oxygen and not all of the other particulates. If they breathe the oxygen here in Vegas, they don't have 160 millimeters of mercury of pressure because technically they're not at sea level. So because we are higher in elevation, at the lips they actually have 148 millimeters of mercury at the lips. Now, if you decrease the amount of oxygen at the lips, the pressure of oxygen at the lips, you're also going to decrease the pressure of oxygen at the alveolar level as well as the tissue level, which means if you use general terms, in the alveoli, you lose about 30 to 35% of your pressure of oxygen. Your 148 then drops down to about 96.2 millimeters of mercury. Quite different than the 104 that you actually have at sea level. You drop another 9 or 10% to get down into the tissue level, which means now you're at 87.5 millimeters of mercury. We are still good and actually have plenty of oxygen to allow for aerobic cellular metabolism. But now we're actually going to go up to Mount Charleston. Based on the official elevation of Mount Charleston, the PO2 at the lips is 119.7 millimeters of mercury. At the alveolar level up on Mount Charleston, your PO2 actually drops to about 77.8 millimeters of mercury. And then at the tissue level, you actually drop down to about 70 millimeters of mercury. So as you can see, somebody who comes from sea level and then goes up to Mount Charleston, they're used to having quite a bit more pressure of oxygen. Unfortunately, they don't really have it any more oxygen available to them because they have less pressure. This is very important whenever it comes to putting patients on oxygen. If you were to put a patient on a non-rebreather, you actually increase the PO2 at the lips from 160 millimeters up to, let's just use fun numbers, and say 600 millimeters of mercury of pressure. If you increase the PO2 at the lips, you're going to increase the PO2 at the alveoli, and then you're going to increase the PO2 at the tissue levels themselves. The last thing that I want to talk about here is this picture that's actually located right below the slide, or I'm sorry, right below the table here. First thing I want to actually concentrate on is the left side of the picture. A lot of people have an illusion that when a red blood cell goes and travels through the lungs, it will pick up about 97% saturation of oxygen if your PO2 is about 100 millimeters of mercury in the lungs, which means you're going to be about 97% saturated on your red blood cell. Now, that's a very good saturation. The problem is that a lot of people think that when that red blood cell makes it down to the systemic tissues, that most, if not all, of the oxygen leaves that red blood cell, and that's not entirely accurate. When a person is at rest, and we're looking on the left side of the picture here, if your PO2 is 100 millimeters of mercury in the lungs, that means that you're going to have about 97% saturation of that red blood cell. When that red blood cell actually then travels down here to the tissue level, even though the PO2 in the system level is 40 millimeters of mercury in the interstitial tissue, you don't lose all of your oxygen off of that red blood cell. You only lose about a quarter of it. So you still have 75% of your red blood cell saturated with oxygen. This is actually the oxygen reserves that people talk about. You still maintain some oxygen on that red blood cell in the event that you need oxygen suddenly and not all of your red blood cells can come back and actually reload themselves with oxygen. Now, on the other hand, whenever you start talking about people who are exercising, And now we're actually going to look over here on the right side of the picture. People who actually start exercising, you have an increasing offloading or unloading of oxygen off of the hemoglobin. So you start off the same. You still have a PO2 of 100. You still have oxygen saturation of about 97% of that red blood cell. The problem is now in the system you have a decreased PO2 because you now have an increase in cellular metabolism because this chick here is jump roping. What that means is you actually lose more of your oxygen off of your red blood cell. But if you notice here, you don't lose all of your oxygen off of your red blood cell. In a normal, healthy individual that has a very intact respiratory system, whenever this red blood cell actually travels back to the lungs, it will once again reload up to about 97%. Just because you lose about 70% of your oxygen here doesn't mean that you completely deplete the red blood cell to where you have 0% of saturation on that red blood cell. This 35% here, this also is the oxygen reserves that people will use or that they will maintain in the event that they need even more oxygen. The problem that we run into, or that patients will run into that actually have a respiratory disease, is that if this cell that has 35% oxygen saturation here travels back to the lungs, what happens if there's a pulmonary disease that does not keep this PO2 as high as it's necessary? Well, what's going to happen is this 97% is going to drop, and maybe you're only going to reload up to 75% of that red blood cell. In this case, you're still going to lose a whole bunch of oxygen down in the systemic vascular system, but you're not going to stop at 35%. You're going to be even less than that. And every single time this red blood cell goes back to this diseased lung, it picks up less and less and less oxygen. So whenever they say that you have a respiratory patient who is having significant amounts of trouble breathing and is hypoxic and their pulse oximetry is dropping, what's happening is their red blood cells cannot reload with oxygen fast enough due to the diseased lung. And this is an explanation of where the oxygen reserves come from.